Concepts we're going to look at, Jacob, we're going to revisit it when we do rocket science. We want to talk about work. Work, first of all, it's a scalar. Part of the problem with the word work is it's an English word. People associate work with getting tired. In physics, work has a very specific meaning. It's the product, which means we're going to multiply, of the force component and the distance moved. Work is force times distance. Our abbrev for work is going to be a capital W, force times distance. But there's a restriction. The key is the force and the distance have to be in the same direction. The force and the distance have to be in the same direction. Now, this is the work for a constant force. We'll talk a bit more this year. What if it's a changing force? But first of all, what would the units be? Well, what are the units for force? Starts with letter N. What are the units for distance? Starts with an M. So it's a Newton meter, but this concept is so important, we've actually renamed the Newton meter the joule, named after a scientist. His last name was Joule. Work is measured in joules. Newton meters. Oh, and since a Newton is mass times acceleration, it's really kilogram meters per second squared meters, which would make it kilogram meters squared per second squared, I think. I don't know. So let's start with one right away. Ella, what's example 1 want me to find? Well, right now, work is force times distance. It's the work Amy does when lifting. Underline the word lifting. I'm going to argue, Ella, that the work done by lifting is going to be the force that you do lifting times the distance. Problem is they didn't tell me that. I'm going to do a quick free body diagram right here. Let's suppose that Amy is doing the minimum work possible. As she's causing this to lift up, she's lifting it at a constant speed. She's not accelerating it. If she did that, what would the forces acting on it be? Get the obvious one. Okay. mg. And then we would have F lift. And if she's going at a constant speed, it would be the same size as gravity. So work equals force times distance. The work done in lifting is the force in lifting times distance. I don't know the force in lifting. Oh, but look. I know the force the same size as the force done in lift. Yeah, I'm not saying that when you lift, the work is gravity times distance, because those are not in the same direction. I am saying, in a wonderful coincidence, Presley, it's the same size as F lift. And in fact, what we said last year, you might recall this, Ella, is instead of using D for a vertical distance scalar, we called it H for height. We called it MGH. It's going to be 50 times 9.8 times 5, which is what? How many joules of work? 2450? Is that a lot? 1 joule is not very big. This is a fair bit. To put this into perspective, 50 kilograms, that's about 120 pounds. That's a medium-sized, small-sized person. 5 meters would be about 1.5 stories. This would be how much energy it took to piggyback somebody up 1.5 flights of stairs. Could you do it? In an emergency, you could, to save someone's life in a fire if they were unconscious or whatever. Would you like to do it? Probably not. You'd be, if I got a choice, I don't feel like carrying somebody up 1.5 flights of stairs. I will if I have to. Okay. What if Amy can't lift it straight up? She's not strong enough to do mg. Well, she decides to push the mass up a ramp at an angle, did I say angle, of 30 degrees. If the mass ends up as the same height as before, how much work will she do? Let's assume there's no friction. It says dolp. Let's draw a ramp. And I'm going to do this generically. Instead of putting 5 meters, I'm just going to label that with an H for height. Instead of putting 30 degrees, I'm just going to put a theta there, color. And let's suppose, Riley, we're partway up the ramp. She's pushing it up the ramp. She's got partway up the ramp. What are the forces acting on it? Get the obvious one. Thank you. Really? The obvious one, gravity. Is there an angle? Pause. Components. Here's mg perpendicular. Here's mg parallel. Color, 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 color. What else, Riley? If this was all there was, which way would this accelerate? Down the ramp. Oh, let's assume she's pushing it up the ramp at a constant speed. So we'll call this F applied. How big is F applied exactly? The same size as? It's going to be the same size as mg parallel. Okay, so let's do this generically. The work done pushing up the ramp is going to be F applied times distance, and that's going to be the distance along the ramp. I'll call it d ramp. That's going to be this distance, but I'm not going to draw it in just yet. It's going to clutter up my diagram. I don't know F applied. Oh, but look, Chantel, I know another force that's going to be the same size as F applied. Which force? mg parallel, 2 lines, everybody? Okay, this is going to be mg sine. Don't drop the d ramp down yet, though. I want to look at that. I'm going to redulp my triangle, but this time I'm not going to think of it. That's a terrible triangle, Mr. Dueck. This time I'm not going to think about it in terms of forces. I'm going to think about it in terms of distances. So there's h for the height. There's d. There's theta. Color, color, color. This h is height, not hypotenuse. Unfortunately, we're running out of letters. So the height, not the hypotenuse, opposite, adjacent, or hypotenuse. How about here? Which trig function? Yeah, I get this. I get sine theta equals the height divided by the distance. I want to get the distance along the ramp because that's d ramp. How would I get the d by itself? Where is the d right now? On the... Bleh! Wait a minute. I can multiply the d to the top, divide the sine theta down. I think d is going to be sine theta. No, not sine theta. It's going to be height divided by sine theta. Jesse, you okay with that? This is d ramp. I'm going to stick that right there. I'm going to get h over sine theta. Presley, do you see it? What happens to the sine thetas? Yeah, in fact, here's the nice thing about work. It's a scalar. That MGH will work no matter what path you take, whether you lift it straight up or whether you did a path like that. As long as you end up 5 meters above where you started from, it's MGH. What this means is this is going to be a really good tool to analyze from the side things like roller coasters that have curvy slopes. By the way, we call this ramp, this is an example of what we call a simple machine. What's a simple machine? It's some device that says, how much work do you need to do? Oh, you can't apply the force? We'll increase the distance, reducing the force. It reduces the amount of force required, but the trade-off is it increases the distance. You still do the same amount of work. And in fact, we just proved it algebraically that a ramp will do the same amount of work. But what you'll do as distance gets bigger, the force gets smaller. Joe, you just got to push it for a further distance, but you don't have to push as hard. The Egyptians built the pyramids with just this technology. As far as we know, they didn't use wheels to move the blocks into place. They built ramps They wet the sand down with water to reduce the coefficient of friction, and they pushed. And as long as you build the ramp fairly shallow and you're willing to push it a long distance, you don't need that big a force to move a huge block. And you don't need aliens or whatever garbage you're seeing on TV. Pyramids are perfectly doable with humans. Another good example of a simple machine is how a screw and a screwdriver works. So a screw head is only about that big. If you tried to turn it with your fingers, you really only want to move it one circumference, which is about that distance. But to move it that distance, you need a big force. Or you can use a much larger screwdriver. Now you're turning it that distance. You need to turn it more of a distance, but you can have a much smaller force. That's what a screwdriver does. It's a simple machine. A screw is considered one, I think there's 6 simple machines. I can't remember. There's some debate as to, but the wheel, the screw, the lever, the ramp, the wedge. I think the pulley is the last one. They're all clever ways where you can increase your distance, reduce your force, same amount of work. If there's friction on the ramp, you end up doing more overall work, but the force is going to be still way smaller than lifting it directly. That's what stairs are. We could, instead of building stairs, just install ladders everywhere. That would force all of you to do the work as MGH. Or, you know what? We can put a shallower stair. You can walk up the stairs casually. You don't even notice how much work, how much force is required. You can carry on a conversation. But it's a much bigger distance than just going straight up a ladder. A ball on the end of a rope is following a circular path because of a constant force exerted on the ball on the rope in the direction toward the center of the circle. Say what? Look up. We're talking about this. Okay? We're spinning a ball. Sorry for those of you on YouTube. We're spinning the ball around our head. It's on the end of a string. How much work am I doing? Well, this is a bit of a trick question because the force is in that direction toward the center, but the distance is in that direction. The amount of work, 0. No work is being done in our physics definition because the force and the distance have to be in the same direction. Now, you can have negative work. A force in the same direction as motion has positive work. A force opposite to motion, like that one there, does negative work. The negative work isn't direction, Aaron, it's magnitude. What we would say if you're doing negative work, the object is losing energy. If you're doing positive work, the object is gaining energy. So even though you might think, isn't that a vector? You're talking about directions. We're talking about magnitude, losing and gaining. So although work can be positive, it's not a vector. It's a scalar. It has no direction, much like your future. Okay. Well, spoiler alert. What if we pull at an angle? Did I say angle? So here is one. We have a child pulling on a wagon. How much work are they doing? I think we'll find it easier. Let's extend the F a little bit. We'll call that F. It is F applied, but I'm going to leave the applied off because I'm going to do as generic a diagram as possible. We are at an angle, components, so we would go like this. D, 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 D. This would be Fx. This would be Fy. Color, color, color. Which of those 3 components is in the same direction as the distance? Look at the picture. Fx. So we would say this, work equals Fx times distance. Which trig function is Fx? This is a lawnmower question in disguise. Does anybody remember? Because it was on your test. Of course it is. Work equals the main force times distance cos theta. You could have put the cos after the F, but that's how it's traditionally written. This is actually the better formula for work. Work equals force times distance cos theta. Can you do me a favor on your blue sheet next to where it says W equals FD? Add that. Not on your yellow sheet, on your blue sheet. Did we just finish doing a unit where we had lots of components and parallel and perpendicular? Yes or no? Yes. And the previous unit, when we were doing projectiles, did we do horizontal and vertical components on almost every projectile question? Yes. You know what? I will, in the homework, you might see the odd force at an angle. Did I say angle components? I'm not going to on your quizzes or on your test in this unit. I'm going to keep everything linear. I've flogged components enough. But by the way, what if theta is 0 degrees? What if the force and the distance match? On your calculator, what's the cosine of 0 degrees? Oh, and then you get force times distance, just like I told you. What if we're at right angles? What's the cosine of 90 degrees? 0. That's why up here there's no work being done, because if you went force times distance cos 90, 0. So one definition of work, force times distance. You can add the cos if you want to. There's actually going to be 3 definitions of work. 2 of them are on your formula sheet. One you're going to have to memorize. This is the one you're going to have to memorize. What if the force is not constant? What if it's changing? Second definition of work, it's also the area underneath a force versus distance graph. How will you know to use that definition, Carter? There's going to be a graph. Oh, and by the way, I will be giving you a question on your test that has a graph. So, Alfie, what is part A asking me to find here? It's off in the margin. What is it wanting me to find? Read the whole thing. Okay. Do you notice they gave me a force versus distance graph? What are we moving from what to what? Everybody, draw a little dotted line vertically above the 2, draw a little dotted line vertically above the 6, and then put your pencils down temporarily and look up. Okay? The work is going to be, don't write this down, this area here. What shape is that? It has 2 parallel sides and 2 non-parallel sides. What do we call a 4-sided shape with 2 parallel sides and 2 non-parallel sides? It starts with letter T. TR. It's a trapezoid. Does anybody know the equation for the area of a trapezoid? Now I'm looking at Ethan. Do you know the equation for the area of a trapezoid? Sorry? You know the English version? Okay. Most students don't know it. The odd time I'll have an international student that knows it. The reason we don't bother teaching it is it's redundant. Write this down. Every trapezoid can be broken into a triangle and a rectangle. And those ones you have learned the area equations for. Those ones are fair game. Alfie, what did this question want me to find? Well, I'm going to call this area 1. I'm going to call this area 2. The work is going to be area 1 plus area 2. Let's find area 1 first. Alfie, what shape is area 1? What's the equation of a rectangle for area? This I will expect you to know. What's the formula for the area of a rectangle? Length times width or base times height. It's really the same thing. I'm going to use base times height for a reason. You'll see why in just a second. Alfie, look at that rectangle. What's the base of that rectangle? How long is the base? How did you figure that out? You're right. Yeah, in other words, just make sure you look at the scale. If it's been going up by 2s, every once in a while I'll have kids, they'll just count the square. No, they're going up by 5s. It would be 20 or whatever. Yeah, in this case, 4. What's the height of this rectangle? I think that's meant to be 2. It's a lousy drawing by Mr. Dueck. In your head, what's the area of the rectangle without a calculator? Okay. And technically joules. Now we want to find area 2. Alfie, what shape is area 2? And do you know what every triangle is? Don't write this down, but look up. Every triangle is half of a rectangle. The area of a triangle, if you know the rectangle, you know the triangle. It's the base times the height divided by 2. Can you look on your formula sheet on the back page where there is a picture of a triangle? Did I give you this one? Or did I finally remove it? I can't remember. I think there it says half the base times the height instead of base times height. Same dealio. So, okay, fine. I guess you don't need to memorize the triangle. You got to know the rectangle. It's length times width, or it's base times height. In this case, Alfie, what's the base of the triangle? I think it's still 4, yes? What's the height of the triangle? Starts at 2, ends at 3. Divided by 2. In your head, what's 4 times 1 divided by 2? You. What's the total work done in this question, moving from 2 meters to 6 meters? What did that work do? Probably went into making the object speed up. Because we have a changing force. By the way, you can see we have a changing force, Alfie. It starts at 1, it ends at 3 newtons. This is not a constant force. This is one of the few ways that we can handle a changing force and therefore a changing acceleration. This would be an acceleration that was changing, because if F equals ma, if F is changing, A is changing. Or maybe the mass is changing, but probably the acceleration is changing. Yeah. Let's talk about energy. Energy is the ability to do work. There are many, many, many forms of energy. One is the energy of motion. Does anybody remember what we called the energy of motion last year? This is kinetic energy. Heat is a form of energy created by friction. In fact, heat is the work done by friction. It's another way to think about it. Gravitational potential energy, that contains 2 words. Potential, stored energy. Gravitational, because of changing an object in a gravitational field or lifting an object. This is stored energy when lifting an object. Potential just means stored energy. So there's chemical potential energy, gunpowder, or the food that you eat that has stored chemical energy. That's where you get your energy from. There are many others. Sound is a form of energy. Elastic energy. When you stretch an elastic, you're doing force times distance. You're storing energy in the elastic. Nuclear energy, the energy stored in an atomic nucleus. There are many, many, many types. We're going to talk about 2 main types. The first type we're going to talk about is kinetic energy. Sometimes when we do work, when we apply a force over a distance, we make things move. It says fill in the proof below to find an expression for kinetic energy. You might remember it from last year, but if you want me to prove it, I would start with our definition of work, force times distance. Then I would say to myself, F equals what? I could write this as ma times distance. Then, Chantel, I'm going to get a bit clever. I'm going to write this as 1/2 m2 ad. I multiplied by 1/2 and I multiplied by 2. Does that change anything? What is 1/2 times 2? Yeah, I've multiplied by 1. Will that change anything? But I did that for a reason. Put a bracket around those 3. Vf squared equals Vi squared plus 2AD. Yosef, get the 2AD by itself. Get the 2AD by itself. In fact, what we can say is 2AD is the same as VF squared minus VI squared. There's this 1/2 m still in front. And if I start from rest, if VI equals 0, I get 1/2 mv squared. There, kinetic energy. M is the mass, V is the speed. That squared dominates your life in many, many ways that you're just unaware of, and I'll try and make you aware of some of them. But that squared has a huge impact on all of you. In fact, later on this year, I'll be giving you a bonus challenge where you can earn an extra mark on a test, but the challenge includes the squared, which is really going to come back to bite you. What do you mean? I'll tell you when we get there. 1 joule is really small. My love of all things trivia. A jelly donut has about 10 to the 6th joules. There's a small measure of energy called an erg. That's about the equivalent of a mosquito doing a push-up. It's 10 to the negative 13 jelly donuts. It's about 10 to the negative 7 joules. It's a really, really tiny unit of energy. It's one that shows up on the atomic level when you're talking about how much energy electrons or whatever gain or lose when they're jumping shell. It's a really small amount. You don't need to know those two. That's just nerd trivia. But already now we can say this. Suppose a golfer wishes to improve their driving distance, how far the ball goes when they hit it. What would have more effect? Doubling the mass of the club or doubling the speed of the club head? What'll give you more bang for your buck? Why? Okay, because we have a v squared, if you double a v and then square it, you'll have 4 times the distance. Roughly, let's assume we're not losing anything to friction. In real life, it's not quite that simple, but in our magic physics world, yeah. This is why, and I think I mentioned this to you last year, over the last 30 or 40 years, as materials science has gotten so much better, equipment has become lighter, not heavier. Golf clubs are way lighter than they were 40 years ago. The tennis rackets they have nowadays, compared to the ones that I played with when I was in high school, the ones that I played with when I was in high school, they feel like cast iron frying pans now. I can barely move them. They feel so heavy. Now, there is a trade-off. There is an m in the equation, Adam, but the increase in speed that you get more than makes up for it. Hockey sticks have gotten like tennis rackets, golf clubs. Baseball bats, no, but that's because the baseball bat mass is a rule. It has to have a mass of between thus and such and thus and such. And I'll change that. But pretty much any other sport where you strike something, the objects have gotten lighter. Yeah, because of the squared. Sometimes when we do work, we lift an object and we give it height energy. You know what? We already figured it out when we did the very first example. When you lift something giving it gravitational potential energy, what is it? It's mgh. It's mgh. Pause the video for just a second. The height, it's above whatever your surface is. It can be positive if it's above. It can be negative if you're going into a hole. You can have a negative height. You can be losing energy. We focus on mechanical energy mostly this year, which has 2 main types, kinetic energy and potential energy. And the potential, the stored, usually going to be gravity, but not always. This brings us to the whole point of this lesson. This is, you want to sit up. This is the most important part. This is the work energy theorem. Ooh, Alfie, what was the equation for work? No, actually, you weren't the one I picked on. Ella, what was the equation for work? The first one. Work equals what? And I always try force times distance first because, no pun intended, it's the least amount of work. It's also the least useful. It only functions in certain situations. The second definition, the area under a force versus distance graph. How do I know to use that one? There's going to be a graph. It's going to be fairly Captain Obvious, Anderson. But the third and best definition, but also the most cumbersome to use and to write, is what's called the work energy theorem. This is what links work and energy together. It says the net work on an object is equal to its total change in energy. What? As an equation, the work equals the change in potential energy plus the change in kinetic energy, where delta change in is equal. What's change in anything? Did I put that on your formula sheet or not? I did in physics 11. I didn't in physics 12. You need to know that. Okay. Oh, some textbooks will assume that you're doing the work energy theorem over level ground, which Caden would mean you're not changing height at all. So some textbooks will tell you the work energy theorem is just the change in kinetic energy. Well, I think I disagree with that. I think it's the change in potential plus the change in kinetic. And I believe, correct me if I'm wrong, I gave you this version on your formula sheet, did I not? Okay, the work energy theorem. This is, by the way, Caden, going to become, in a couple of units, the rocket equation, the rocket fuel equation. If you want to know how much rocket fuel it takes to put something in orbit, you start with this. Unfortunately, it's going to be rocket science. What do I mean by that? It ends up being almost a whole page, about 15 lines of writing, but it's cool. And I hope you weren't expecting rocket science to be easy. There's a reason why they say it ain't rocket science. They mean rocket science is tough. But we will revisit this several times in the future. Okay. Put your pencils down, look up. I showed this last year, but I'll re-show it here because it's a nice example of the work energy theorem. I want physics 12, Mr. Dueck. So a slingshot is a really nice example of stored energy. Not stored
Just pull the suit out. Be ready for, like, it's going to spring you forward and it's going to want to, kick you back. And if you're just like a super and just your body's tense towards this way, like an arrow. Some people do, some people don't. I think you know.
All right, have fun.
Un, deux, trois.
Have we applied a force, Ethan, look up, over a distance? Have we applied a force over a distance? Yes. Have we done work? Yes. Have we stored some energy into her system? Yeah. What type of energy? Yeah, probably elastic potential if we wanted to include the stored. What's it going to get turned into? Very kinetic. This video, I think it's from Utah. I would have a bit of a concern because she starts out almost vertical. I would be really concerned about whiplash or back damage. But I've read online, I think there's a resort in Minnesota that does offer this, but you're horizontal in their setup. You've got a back brace that you're wearing, and you got a neck brace and a helmet and pads that you're wearing. Then I'd probably be willing to try it. I've also seen a version of this at some amusement parks. I saw one in Orlando. Their version, though, the slingshot was a vertical slingshot. They had two big towers with bungee cords, and there was a large caged-like ball, a ball in the shape of a cage in the shape of a big ball, enough to fit two people in. The two people would get in, get strapped in with their backs facing the ground, so with their bellies and their faces facing up. They would winch the ball down, tightening the bungees, and then when they released them, the ball would bounce up and down like a yo-yo for quite a bit. That one I think I would try as well, because there you're nice and supported, you got a good neck rest, so you're not going to get whiplash. That one I'd be willing to try if I ever see it again. I like example 8, I like example 8. Example 8 is a nice question. Joe, what's example 8 asking me to find? How much work? Don't write this next bit down, just watch. My first thought would be to try going force times distance, because that's the least amount of work. Don't write that down. Read the question. Is there a force in newtons? Is there a distance in meters? And so my brain would think that and go, well, would have been nice. Then my next option would be if they had given me a force versus distance graph and they wanted me to find some area. Did they give me a graph? Be stupid obvious? No. So only then would I pivot to the most useful but the most cumbersome, the most, no pun intended, work of the work equations. Work equals delta PE plus delta KE. You're going to have a change in potential energy if the question gives you a change in height, because that's what has to happen for gravitational potential energy. Do you see a change in height in here at all? So I think I can go like this. I think the change in potential energy equals 0. I do see a change in speed, though. I think there is going to be a change in kinetic. What's change in anything? It's going to be KE final minus KE initial. I agree. Work is going to be, oh, can you all underline the word stop? What does stop tell me? What's 0? Joseph, what's 0? V final. And if V final is 0, what else must be 0? Yeah, you know what? That must be 0 because of stopped. So what I end up with, this one cleans up a little nicer than a lot of the work energy theorem equations do, with negative a half mv initial squared. Negative 0.5 times 1200 times 32. Don't forget the squared. What do you get? I don't know. Hang on. Other people are still typing. But thank you for your enthusiasm. There, Aaron picked up his calculator. Now he's going. Joe, what did you get? Read me the digits. Negative 6. 3 zeros? Is that right? Is it 3 zeros or 2? Double check to make sure you didn't miss the decimal in front of the point. Okay. Got to be a little impressed that I predicted that. So 2 zeros. So a little more than 500,000 joules. What's the negative telling me? The car has to lose that energy. Where does that energy go? Yeah. It heats up the brakes for an internal combustion engine. Where does it go for a hybrid or EV? A big bunch of this goes back into recharging the batteries. This is why hybrids and EVs get so much better, I'll call it gas mileage, even though it's electric mileage, in city driving, because every time they're coming to a stop, an internal combustion engine, that's purely wasted energy. But on a hybrid, you're capturing a fair bit of that back. It's not 100% efficient, so it's not perfect, but you're capturing some of that back. Yeah, it's why all the taxi drivers, they all drive Priuses now. It makes so much more sense for them economically. Drops their fuel costs dramatically. My friend has a Chevy Volt, and he took it from the top of the Coquihalla down to the bottom of the Coquihalla. And when he arrived at the bottom, his batteries were fully charged. At the top, he'd started with about 3/4 of his batteries. So he picked up all that charge just because he's losing potential energy. That energy's got to go somewhere. Some of it goes into kinetic, but once he stops speeding up, that energy's still got to go somewhere, goes into recharging his batteries. Example 9. Example 9. Carter, what's example 9 asking me to find? So again, don't write this down. My first thought was to go force times distance. I mean, I kind of see a distance there, but I haven't dealt with that speed. I don't exactly see a force. I think I'm going to use the work energy theorem. I think I'm going to use work equals delta PE plus delta KE. What's change in anything, Carter, my friend? And how do I find gravitational potential energy? What's the equation? On your sheet, PE equals. Yeah, now you're going, oh yeah. So I think, do you agree with me? It's going to be mgh final minus mg. There's my h initial. There's my final minus initial. And then big plus sign. What's my equation for kinetic energy? So it'll be a half mv final squared minus a half mv initial squared. Usually right around now, I ask, are any of these zeros? Where would mgh be zero if h was zero, if we were on the ground? Are we ever on the ground, Carter? I think I agree with people who are saying, Mr. Dueck, we're starting out on the ground. Are we not? Because the cannon's on the ground? Is that okay? Where would kinetic energy be zero if we're at rest? I think we're starting at rest before we pull the trigger. In other words, all of the energy that this cannonball got came from the gunpowder. The gunpowder is what did work. What are we going to get? Let's crunch this. The work is going to be 19 times 9.8 times 245 plus 0.5 times 19 times 95 squared. mgh final plus a half mv final squared. This would be the artillery shell work equation. What do you get? Positive or negative, first of all? Yeah, the shell has to gain energy. Positive, what is it? And then some decimals, if I recall, yeah? So 131,000 joules. By the way, when the shell hits its target, what's its final height? Be obvious. When the shell hits its target, what's its final height? Be obvious. Okay, artillery shell, boom. When it hits its target, what's its final height? Be stupid obvious. 0. What's its final speed? Be stupid obvious. So it's lost all that energy. Where does that energy go? Destroying the target. It's, by the way, I need to change these numbers. 95 meters per second, that's a pathetically slow artillery shell. Most of them go faster than sound. Most of them have a 300 or a 400 something here, which would get squared. It's why, even though in modern weapons we have all these smart bombs, artillery shells are still used by modern RVs. They're cheap and they're effective, baby. Yeah. Last one. I like example 10. I like example 10. I like example 10. Example 10 is a nice question. Okay. Anderson, what's example 10 asking me to find? Huh. How fast? Did they give me a graph? What kind of a graph? What's what on the y-axis? What's on the y-axis? What letter? Not FN. F in newtons. What's F an abbrev for? So what's on the y-axis? What word? What's on the x-axis? This is a force versus distance graph. That's a hint. I think we're going to be using area. That's a hint. Now, I like this. Did I say I like this question? I like this question. I'm emphasizing that on purpose, boys and girls. Pick up on the hint. Okay? This is asking how fast, and my normal strategies of saying V equals question mark aren't going to work because there's not much data here. Instead, I need to realize I'm going to solve this using work, and I'm going to write the most obvious question, the most obvious equation ever. You can't argue with me on this. I'm going to write work equals work. Booyah! That's got to be right. What I'm going to do is I'm going to write work in two different ways. On the left, let's do the area. How fast is it traveling after? What's the distance they gave me? So let's go to 0.8, and you can do a dotted line, d, 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 and I guess we want this area here. What shape is that area? I want the area of a triangle. How do I find the area of a triangle? Base times height divided by 2. Drop your equal sign down again. What's the base of this triangle? How long is it? Look at the graph and figure it out. 0.8. What's the height of the triangle? Good. Not 8. What my last class said 18. No, look where the point is. Read across. 16 divided by 2. We'll fill in these lines in a second, but let's drop one more equal sign down. Is it 6.4, I think? 16 times 4 will be 64, so 0.4 times 60. 6.4? That's how many joules of work. Okay. On the right-hand side, we're also going to write work. What were they asking us to find? I'm going to use the definition of work that had a speed in it. I'm going to use the work energy theorem. I'm going to go change in potential plus change in kinetic. Now, although I said I like this question, I like this question, I like this question I would not allow on the test unless it contained this phrase, over level ground, or assume the ground is level, or over a flat surface. I have to assume that in this question. I will tell you that if I give this to you on a test, okay? If the ground is level, what's the change in potential energy as a number exactly? 0, because there's no change. By the way, I could, for giggles, put this on a hill, and as long as you knew the height you started and the height you finished, whether it was uphill or downhill, not much more typing. But yeah, this is going to be 0 because we're on level ground. What's changing anything? What's the final kinetic energy here? I don't know. What's the initial kinetic energy? See it? I should have underlined that phrase there. If we're starting at rest, what's our initial? Yeah, so what I'm going to do in our notes, I'm going to expand this into KE final minus KE initial, and then I'm going to go, haha, equals 0. But if you were clever enough to just see that and go straight to the next line and say, you know what, it's going to be a half mv final squared. In fact, it's going to be mv squared over 2 if I write it like that. How would I get the v by itself? By the way, I could also tell you the speed and ask you to find the mass of the object. Yes? Get the m by itself. Get the v by itself. How will I move the m over? How will I move the 2 over? And then? Yep. V is going to be 2 times 6.4 divided by, and what was the mass? I've scrolled down. Oh, 25? Square root. I have no idea what the answer is here. What do you get? 0.716. Anybody else? People nodding? Units? Direction, it's a speed, it's a scalar, no direction, much like your future. No direction. So here's a nice one where they didn't give us much information, it seemed, but from the graph and a bit of cleverness, I was able to now derive an awful lot. What's your homework? Here's what I assigned my block E's. One is good, two is good. You could skip number 3. Hey, there is, yeah, okay. 4 is good. Put a star next to number 4. Part C, you need to read very, very carefully. By the way, they're using kilojoules because 1 joule is so small. You will occasionally see kilojoules. How many joules is 1 kilojoule? 1,000. So if I'm going from kilojoules back to joules, divide by 1,000. I'm going from joules to kilojoules times by 1,000. Is that right? Other way around. I said that backwards. You can skip 5. 6 is good. 6 is walking you through what we already did with the ramp, where we noticed that for a ramp, whether you push it up the ramp, how much work, or how much work lifting it to the top of the ramp, you still get MGH no matter what. So it's asking you to kind of reprove that. Why did I circle answer 2 for number 7? It says, which of the following best represents the kinetic energy of a freely falling object as a function of time? What's the equation for kinetic energy? Half mv what? Half mv what? Oh, it's going to be a parabola. Squared. So got to be that one. So we did that one already now. 8, 9, 10, 11. Skip 12. 13, skip 14, 15. It's good. 13, skip 14, do 15. And you got 12 minutes. Please use this, especially those of you that are on Santa's workshop list. You know who you are.